everybody. Thank you very much for being here. My name is Nadav Cohen. I'm from the Hebrew University of Jerusalem, and today we're going to be talking about semantic segmentation in art paintings, a work done by me together with Yael Newman from Tel-Aviv University and Professor Ariel Shamir³ from Reichman University. We're going to be talking about a few subjects today. We're going to start with a brief background on art and neural networks and domain adaptation for semantic segmentation. Then we're going to proceed to DRUM, the dataset we built for semantic segmentation of art paintings, our approach for semantic segmentation of art paintings. We're going to show some experiments, results, and applications, and we're going to conclude with limitations and a brief summary. Semantic segmentation is the task of predicting a pixel-wide classification for a given image X in a finite set of classes. This task has many approaches, like the Deep Lab networks by Chen et al., and as we can see, for photographic datasets, they achieve very good results. The problem is, when trying to generalize over art paintings, these networks fall short. The question I want to ask you here is, what makes paintings so different than photographs? Paintings and photographs have a few noticeable differences, like color and texture differences, where paintings may have unrealistic colors and unrealistic textures, which are caused by a creative use of a painting brush. Content differences, wherein a realistic scene can be depicted with an unrealistic motif, like a dark motif or a religious motif. And geometric differences, where figures can be depicted with a strong geometric distortion or an unrealistic shape. Given these differences, can we rely on current research to help us overcome them? When looking at current research of art and neural networks, we can see it's mostly dominated by generative models. Noticeable examples are StyleGun, which can create artistic portraits of people, and many style transfer approaches, where a style of a painting is transferred to a photograph. Unfortunately, when it comes to perceptual tasks, we mostly see classification works. Additionally, we don't see too much attention to the deep and delicate difference between art styles. So given that we don't have segmentation labels, and we don't have too much to rely on from previous work, we were looking for an unsupervised approach to start developing our method. This led us to domain adaptation. The main concept of domain adaptation is you want to optimize a task over an unlabeled domain by using its commonality with another labeled domain, in our case, unlabeled paintings and labeled photographs. We'll be seeing two main concepts of domain adaptation. The first, image-level augmentation, where we want to change the source labeled dataset to look more like the target unlabeled dataset before training. The second is called feature-level domain confusion, where we use a discriminator in order to teach the encoder of the segmentation network to encode the source and the target features into a shared feature domain. Hopefully, this shared feature domain will be reliant on the commonality of both domains. Before we dive deep into the specifics of DRUM dataset and our method, let's talk a little bit about the motivation for this work. Why do we care if computers understand art? First of all, we think this is a very interesting task to solve, given that some people have a hard time understanding art. Teaching a computer to understand art is a very interesting way to push the limits of computer perception. Second, solving a task on a more complex domain may give birth to new and creative solutions, which then can be applied back on the easier domains and improve them even further. Finally, improving the perceptual art abilities of a computer may lead to the computer being a better artist, thus improving also generative models on the way. Hopefully, on the end of this lecture, we'll convince you that all of these points are true. Now that we have our motivation, let's talk about DRUM dataset, a domain adaptation dataset for semantic segmentation of art paintings. DRUM is the initials of diverse realism and art movements, which puts an emphasis on the diversity of the realistic aspects of the art movements of DRUM. We use 12 classes, which are more common in art paintings, like people, animals, house objects, boats, and more. We collected almost 6,000 train images and almost 600 fully annotated test images from 4 main art movements: Realism, Impressionism, Post-Impressionism, and Expressionism. Additionally, we collected 135 test images from 8 different art movements which won't be seen during training. Let's have a closer look on the art movements of drum. Realism is an art movement which tries to portray situation as realistically as possible. Its artistic properties are it's realistic in textures, colors, and geometry. Impressionism is an art movement which is characterized by relatively small, thin, but yet visible brushstrokes which give it an unnatural texture, although it still puts an emphasis on an accurate depiction of light. Its properties are unrealistic textures, but realistic colors and geometry. Post-Impressionism is a movement which emerged as a reaction against the Impressionists' concern for a natural depiction of color and light. Its artistic properties are it's unrealistic in textures and colors, and it starts also to be a little bit unrealistic when it comes to geometry. Expressionism is an art movement which sought to express the meaning of emotional experience rather than the physical reality in a painting. Its properties are it's unrealistic in textures, colors, and geometry. As mentioned before, we collected paintings from 8 art movements which are absent from the training set. We created this unseen test set to validate that our network learns artistic features rather than overfitting on specific movements, and that it can use this knowledge to generalize over new art movements. The ability to predict good segmentation maps for unseen art movement is also practically important, as some art movements don't have enough examples to hold a learning process on their own. Now that we know drum dataset, it's time to present our method, and we'll start with a general description of the training flow. First of all, we train a separate segmentation network for each of the art movements, so we can learn their unique characteristics. This is important, as trying to optimize over all art movements at once results in a highly variable domain, which in return hurts the optimization results. The first training step is an image level augmentation step, where we apply style transfer on the source photographic labeled set with random paintings from drum training set, and then use these images, which we call pseudo paintings, for supervised training. The second step is a domain confusion step, where we optimize an adversarial task where we train the encoder to map the photographic and artistic features to a shared feature domain, unrecognizable by a domain discriminator. Let's talk a little bit more on each of these steps. In the first step, we go over the source and target domain and pick random couples. Let's say we got a cat and an impressionistic painting. Then we run the images through a pre-trained ADA-in-based style transfer network to get this impressionistic cat, which again we call pseudo-painting. Then, as this cat is based on a source labeled dataset, we can use it to do supervised training on a segmentation network using the original ground truth label. After we do that with the entire training set, we can go over to the next step. While still training a segmentation network on the source labeled dataset in a supervised fashion, we also add a discriminator which discriminates between features of the source and the target datasets. While the discriminator optimizes over how well it discriminates between the source and the target features, the encoder optimizes over its success to confuse the discriminator. The important thing to say about this discriminator is it's not a regular discriminator which discriminates between domains only. It discriminates by domain and class, and it does discrimination prediction also per each pixel of the image. We use this fine-grained discriminator as it's been found robust to domains with a high class variability. On this slide, we see the entire training flow. We start from training the style transfer network and then using it to create pseudo-painting datasets for each of the styles, which then are used for supervised training on the segmentation networks, and finally, a domain confusion step. The next question I want to ask you is, now that we have 4 segmentation networks, one for each style, What do we do when we want to predict a segmentation map for a new input image? Before I answer this question, I want you to put 2 points in mind. The first point is paintings may come from unseen art styles, which means there may not be a perfect decision for a single network for an input image. The second point is paintings may combine elements from many art styles, which means we may benefit from using more than one network for the solution of an input image. Putting this in mind, the main idea is we want to find a style representation for the input image and compose the network solutions based on the closeness of this style representation to each of the styles of the networks. We use the gram matrices as style representation as they were shown by Gattis et al. In his style transfer work to be a good representation of the style of an art painting. So, we input the image through all the segmentation networks while we find its gram style descriptor. Meanwhile, we find the gram style descriptors of the entire drum training set, and then we find the k-nearest neighbors in this space. Based on the number of neighbors of each of the styles with the gram style descriptor of the input image, we can create a weight vector, and then we can use these weights in order to compose the solutions of all the networks and get a final solution. So, why is this method actually better than just choosing an optimal network for the input? First of all, it enables flexible predictions for unseen art movements, and its superiority here is proved by the fact that the unseen test set results improve by almost 4% over the best single network scenario. The second point is, this method improves also the results for the original drum art movements. This proves our claim that art movements share their features, although they have their differences. Now that we know how to train our networks and how to inference a new image, it's time to see some experiments and results. Let's start with a few details. We chose the segmentation network named DeepLab V2 with the ResNet 101 backbone. Our evaluation metric is the mean intersection over union, and the source dataset is Pascal Vogue12 after being filtered to have only the 12 classes used by drum. Our target dataset is of course drum. Here we can see some quantitative results. At the top part of the table, we can see the baselines presented at the beginning of the lectures of DeepLab V2 and DeepLab V3 Plus segmentation networks. At the middle part, we can see some competitive benchmarks of recent domain adaptation frameworks. At the bottom part, we can see a variety of our method, where at the bottom row, where we have our full method, we can see that we have the state-of-the-art results, not only for drum dataset on average, but also for each of its original art movements, and also for the unseen test set. Here we can see qualitative results from the impressionistic and post-impressionistic test set. First of all, we can see on the left and the right the input painting and the ground truth label. After that, in the first column, we see the baseline of DeepLab V2, and as we can see, its result is not very good. The second step, which shows the results of our first step without the second domain confusion steps, shows how the network already understands more artistic concepts and can localize objects in the image. The second step, which is our full method, shows how the second step of our method, the domain confusion steps, is able to teach the network specific class features and improve class understanding. This is another example of qualitative results, this time from the unseen test set. As we can see, although these art movements, Fauvism and ink and wash, haven't been seen during training, we still get the same quality of prediction as we saw before. Let's see some applications of our method. The first application I want to present to you is called Comparative Collections. As we can now segment a specific class, we can collect all the segments over different art styles and put them next to each other for comparison. Like in this instance, dogs. We can do this for more classes like people and plants. Our next application is called Semantic Guided Style Transfer. We follow the work of Champandard, who shows how we can use manually labeled semantic maps in order to create a semantic style transfer. Using our semantic segmentation approach, we can create these maps automatically and then create an end-to-end method for semantic guided style transfer. Let's see some results and some comparisons to the classic style transfer method by Leon Gattis, which is the base for Champandard's method. As you can probably see, for our first example, we chose a painting and a photograph of a plant. We can see here the results of our semantic segmentation method, and using these results, we got this prediction. When put next to the prediction of Gattis' classic method, we can see that our method has a much better understanding of the leaf's style. Our next example showcases a photograph and a painting of a dog. As can be observed, in comparison to the Gattis method, our method has a much better match to the fur presented in the style image. Additionally, the Gattis method shows some loss information which is not shown in our method. In this last example, we can see that the horse of our result looks much more like the horse in the style image than the Gattis method. Additionally, the Gattis method kept the white original color of the horse and seemed to be taking the texture of the horse from the background of the style image. Before we conclude this lecture, let's discuss some limitations of our method. The first limitation is we use DeepLab v2 as our segmentation network, which is a bit outdated. As a result of this decision, our prediction may suffer from artifacts as can be seen on the examples on the right. These artifacts are caused because of the naive upsampling manner in DeepLab v2. Our second limitation is our network struggles when it comes to strong geometric variations. This again can be seen on the example on the right, which is taken from the Cubism Unseen test set. Our third limitation is that our method requires prior knowledge of the arc movements of the train set in order to separate them before training. Although this knowledge may be sometime available, it's not a trivial thing to ask for. Our last limitation is that our method is still limited by its number of classes and arc movements, which can always be expanded more. To summarize our lecture, art perception research has not advanced very much over the recent years. For this reason, we presented DRUM dataset, which is a new domain adaptation dataset for semantic segmentation of art paintings, and it can be used for future domain adaptation frameworks as a benchmark. We presented the first semantic segmentation solution for artistic paintings. In doing so, we further explored the challenge of multiple hidden subdomains, which we believe exists in many more data domains. Finally, we applied our results in order to improve applicative tasks such as style transfer, doing so improving also generative models. Thank you very much for listening to our lecture. We hope you found it interesting. We invite you to use DRUM dataset and further explore our method, as our code, checkpoints, and DRUM dataset are fully available on the internet.